Hello everybody, and welcome back to another video on my channel. Today we will once again be talking about another differentiation rule in calculus, which is the chain rule. That's pretty much about it. Let's move on to the lesson. What is a composite function? Now before we start, I'm pretty sure you already know what a composite function is if you studied algebra or looked at some of my algebra videos. Otherwise, all good if you don't know. Basically, what it is it's pretty much one function is applied inside another. And this is just going to be a quick review, as the chain rule is all about differentiating these composite functions. A quick example is h of x is equal to x squared plus 1 to the power of 3. Now an inner function, which is g of x, is equal to x squared plus 1, but then an outer function, which you can say as f of u, is u cubed, where really if we did the whole function, u would be replaced with x squared plus 1. Right before we move on to the actual chain rule, let's look at a few more composite function examples. The first one is h of x is equal to sine 2 of x. The inner function is 2x, and the outer function is sine of u. The same thing goes for the other two. I'll let you read over them themselves, but I don't want to waste too much of your time, so let's move on to the actual formula. Chain rule formula is, if we have one function nested inside another, if f of x and g of x are differentiable functions, then d over dx of f of g of x is equal to f dash of g of x times g dash x. Now, what that means is if we have a function which, when you have one function nested inside another, so basically f of g of x, then that means, first we can find the derivative. First we have to identify the inner and the outer functions. Then we find the derivative of the inner function, that's g dash of x. Then the outer function, we can basically say that g of x is some variable u. Then after that, you can differentiate f of u regardless of the rest of anything else. Just differentiate f of u how it would normally differentiate any function with u. And it's also used in the second definition. I'll touch upon that later. Then it's the same purpose as a dummy variable, and then after you're differentiating and you have f dash of u, then you resubstitute g of x instead of u. Now I know that sounds a little bit complicated, but it will become very clear when we start to do the examples. But right before we start to prove this and do examples, but let me quickly touch up on another way to write this, which is Leibniz notation. Now, what this says is dy by du, basically substituting g of x as u, and then times du over dx, where du is g of x. So that's pretty much how it is. Instead of writing dy over d or df of g of x over dg of x, etc., they decided to have dy by dx just be the whole function derivative. And then what happens after that is we have it with respect to the variable u, so we replace g of x with u, but then in the second part we unreplace or substitute back g of x instead of u, and just differentiate that with respect to x. Let's start proving that if h of x is equal to f of g of x, then h dash of x is equal to f dash of g of x times g dash of x. So the first thing is to start with the limit definition, where h dash of x is equal to limit as delta x approaches 0, where h of x plus delta x minus h of x divided by delta x. Now, I haven't exactly showed this version of the limit definition, but delta x is pretty much h, but since we're using h dash of x, I decided to change it to be just delta x. Now let's substitute the composite function. So we have f of g of x plus delta x minus f of g of x divided by delta x. Now this is probably one of my favorite parts of the entire proof, as it's in fact extremely clever. And when I first tried to prove this myself in general, a long time ago when I learned this, what happened when I figured it out, it was almost like a eureka moment. So basically the thought process behind this was, how do we keep this equation the same, because we can't simplify it anymore, in order to have it be that, okay, we found this, now, oh yes, now we have done it, to figure out that we have one derivative, which is the right side of the equation, and then another derivative, which is the left side of the equation. Delta u is equal to g of x plus delta h minus g of x. And that is pretty much what we mean by multiplying by 1. As you see earlier, over here, we have delta x on the denominator and f of g and so on in the numerator. But over here, we have g of x plus delta x minus g of x times g of x plus delta x minus g of x, where technically it's the same thing, but we just multiply and divide by g of x plus delta x. Now, let u is equal to g x plus delta x minus g of x, and as delta x approaches 0, that means delta u, or just u in general, delta u is equal to 0, assuming g is continuous. Now the final step is to use a limit property to split the limit in two limits. And the first limit, if you recognize it, it'll be f dash of g of x, because technically we have delta u in the denominator, and that's what made it so much simpler. But on top of that, what happens is that f of g of x pretty much becomes the function, and since we have a delta u, and by sheer math, and also by sheer chance, not really, it was all planned out, and it's pretty much very solid in its mathematical rigor, that this becomes the second term. If we replace g of x with x or u, it would be right on there. So that means, and then the right side is just pretty standard, just a limit definition of the derivative, except it's with g of x. So therefore, h dash of x is equal to f dash of g of x times g dash of x. Now let's move on to our first examples / practice problems. So let's find the derivative of y is equal to 3x minus 2 to the power of 4. Now the first thing that we need to do is figure out what is the inner and outer functions. And let's call the inner and outer functions f of x and g of x. F of x, which is the outer function, is, as you see here, we have an inner term, but we also have to the power of 4, so that will be u to the power of 4. G of x, on the other hand, is the inner function, and that will be equal to 3x minus 2, as it's the inside to the power of 4. Now let's state the chain rule. Y dash is going to be equal to f dash of g of x, or we can say f dash of u, then multiplied by g dash of. So with this figured out, let's start substituting. So if we replace g of x with u and just differentiate f of x in general, that will be, using the power rule, that will become 4u cubed. Then what we have to do is we have to multiply this by the derivative of g of x. Now what we have to do after that is substitute u as 3x minus 2. And since we have 4 and 3, that will just multiply to be 12. So we have 12, 3x minus 2 power of, that's pretty much it. It's pretty simple when you do the examples. And that's pretty much the entire solution. Now normally this technically seems like one of the more complicated rules, but in fact it's much easier than it really looks. When it really starts to get hard, it's when we combine it with the product and quotient rule. But that can get so complicated that I can make an entire 20-minute video just showing you step by step how to solve that example, where we have trigonometric derivatives, other derivative rules, the chain rule, the product rule, the quotient rule, and then don't even get me started on double derivatives and implicit differentiation, which we'll cover in our future videos. But when we start combining those, it starts to get really, really complicated really fast. Here is the solution: 12 times 3x minus 2 to the power of 3. Now, the next practice problem is to find the derivative of cosine x cubed. Now, I won't state the quotient rule like last time, but I will explain the inner and outer functions still, because I think that's extremely essential to understand and not to just mess up. The outer function in this, it's going to be cosine of u. And the inner function is going to be x cubed since it's inside another function. Now y dash is equal to first the derivative of the first term, so f of g of x, but really f of u, so I should be calling this f of u, not f of x. Y dash is equal to negative sine u by trigonometric differentiation. Then we have the derivative of x cubed, which is equal to 3x squared by the power rule. So then what we have to do is we have to substitute u in. So this is equal to negative 3x squared times sine of u, which is x. And there you go. There is our second practice problem done. I told you it's still pretty simple. I won't really do anything too complicated this video, but leave a suggestion down in the comments if you want me to do single video covering one really complicated example of everything we've covered thus far. Maybe I'll do it after we figure out the final topics in differentiation, which is the double differentiation and implicit differentiation. Now, I know some of you might be going in the comments and saying, well, what about related rates? What about this? What about that? Those are just applications of derivatives and not actually techniques used to find them itself. All derivatives pretty much can be found out using all the techniques that I've shown above and the two more which we have yet to cover. So maybe after those two videos, if you guys want, I might even if you guys don't comment much, I still might create an example, like one example, very complicated example involving all the rules, just to show you how complicated things can really get, and to show you what's ahead. Maybe they'll have it in an exam or something. Maybe it could be an Olympiad question if you're preparing for that. But I don't know if you're going to watch my videos if you're preparing for an Olympiad. But if you are, then I thank you so much for watching my videos and hope that example in the future will give you a lot of help to solve more complicated problems. But enough yapping from me. This is the solution, and it's pretty much the exact same thing that I said, where we differentiate, multiply, but I just took an extra step saying u and then resubstituting it back in. The third practice problem is to find the derivative of y is equal to the natural logarithm of x squared plus 1. Now, if I haven't covered this already, in the last video for sure, which I covered, I stated that the derivative of the natural logarithm of x is equal to 1 by x, and the derivative of e to the x is equal to e to the x. It's the same derivative every single time. Now, in the future, most likely a video a little bit in the future, I'll probably do a quick proof of both of these just to show you how they work. Now, for e to the x, and for natural logarithm of x, it's a little more complicated. But for e to the x, you're basically substituting e to the x, e to the x, e to the x plus delta x, then minus e to the x as delta x approaches 0. Using exponential properties, it will be really simple to find out. Maybe you can do it on your own, but highly likely I'll create a video in the future explaining how to do it. But let's move on to the actual problem. The outer function f of u is equal to the natural logarithm of x, and the inner function g of x is equal to x squared plus 1. Now, y dash is going to be equal to, first, the derivative of ln u, which is 1 divided by u, then multiplied by the derivative of x squared plus 1, which is 2x. Then, after we substitute, we get 2x divided by x squared plus 1. So that was even simpler than the last example. Pretty much right about it on all we need to do for our practice problem. And here's the solution. Y dash is equal to 1 divided by x squared plus 1 times 2x, which is equal to 2x divided by x squared plus 1. Here are a few additional examples or challenges that you can do at home. Well, most likely you'll be watching this at home, but like you can do it on your own to watching my video, and the solutions are on the bottom right over here. Thank you so much for watching my videos. If you made it all the way here to the end, I thank you so much. I really thank you a lot for watching these videos. If you liked my videos, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And I hope you have a good day. And of course, only do that, only like, subscribe, etc. if you enjoy my videos and found them educational, as it really helps me a lot and gives me inspiration to continue going no matter what happens, because I know I'm making a difference. So please also be free to comment down any suggestions or video ideas you have down below, where it's pretty much like, okay, can you please do this? Can you please do that? I'll try and cover as many requests as I can. And if I have something already planned, I'll just say that I'm doing it in the future. But if I didn't have that plan, I'll definitely try and do it. And so you can stay happy and you can understand more about it without having to look on the web endlessly. So thank you so much. See you in the next one, and bye-bye.